Riemann sums. We assume f is a continuous function on the closed interval from a to b, and f of x is equal to or greater than 0 for all x that's an element of the closed interval from a to b. Choose a positive integer n. We divide the closed interval from a to b into n sub-intervals of equal length. Delta x equals the quantity b minus a divided by n. Set x sub naught equal to a, and then let x sub 1 equal x sub naught plus delta x sub 2 equal x sub naught plus 2 times delta x, all the way to x sub n equals x sub naught plus n times delta x, which equals b. We then have the closed interval from a to b is equal to the closed interval from x0 to x1 union closed interval from x1 to x2 union ... union the closed interval from x sub n minus 1 to x sub n. These sub-intervals form what is called a regular partition of the closed interval from a to b. The endpoints x sub k for k equals 0, 1 to n are called grid points. For each k equal to 1 all the way to n, choose x sub k asterisk in the closed subinterval x sub k minus 1 to x sub k. The x sub k asterisk are called sample points. For k equals 1 to n, construct a rectangle with the base along the closed interval from x sub k minus 1 to x sub k and height f of x sub k asterisk, that sample point. The area under the graph between a and b is approximated by the sum of the areas these rectangles. This is called a Riemann sum. Example: estimate the area under the graph of f of x equals 2x cubed over the interval 0 to 2 using n equals 4 rectangles. Find approximations using right endpoints of the sub-intervals as the sample points. Let's first find the width, which would be the delta x. We do that by finding the difference of the interval and dividing it by the number of rectangles. We go from 0 to 2, so it'll be 2 minus 0, divided by n, 4 rectangles. This tells us that the delta x will be 1/2. Each rectangle will be length 1/2. That's my first step. My next step, I need grid points. So I will draw my interval and mark the starting point as 0, the ending point as 2, and we've got to have 4 equal intervals in there. So we'll have a grid point at 1/2, at 1, and at 3/2. Since we're going to get rectangles, let's go ahead and find the height with respect to the right end. Between 0 and 1/2 for the first rectangle, the right end point is 1/2. So f of 1/2, computing that, be 2 times 1/2 cubed, and that is 1/4. Let's find the height for the next one. Second rectangle, right end point would be at 1. F of 1 would be 2 times 1 cubed. Oh, that's nice. That's 2. Let's compute at the next sample point, which would be at 3/2 because we are using the right end. So 2 times 3/2 cubed, that's 27 divided by 2 times 1/8, so 27/4. And finally, for the fourth rectangle, right endpoint, be 2 times, the endpoint is 2, cubed, which gives us 16. So we found the width, drew and got our grid points, found the height of each rectangle using the right endpoint, and now we can compute R sub 4. That's the approximation of the area under the graph and above the x-axis using 4 rectangles right endpoint. The width is 1/2, so we'll have that factored out, and then add each of the heights. That would be 1/4 plus 2 plus 27/4 plus 16. That sum is 25/2, and you can write that as 12.5. The next part says L4, that's the area approximated using the left endpoint, is 4.5. Make an inference about the actual area A. An inference we can make is that the actual area is going to be somewhere between 4.5 and 12.5. Definition. Suppose f is continuous and f of x is equal to or greater than 0 for all x an element of the closed interval from a to b. Using the preceding notation, we define the area A of the region between the graph y equals f of x, the x-axis, and the vertical lines x equals a and y equals b by a equals the limit as n approaches infinity of the sum of the areas of the rectangles. Let's recall our initial problem. We began with 4 rectangles, solved for right endpoint, left endpoint, and then we looked at 8 rectangles, left endpoint, and right endpoint. Provided for you here, same graph, but with 16 rectangles between the x-axis and the curve. Note that as the number of rectangles increase, as in the definition n approaches infinity, the closer the rectangles become to fitting the actual curve. Sigma notation. This is a notational device for abbreviating long sums, like Riemann sums. Given numbers a sub 1, a sub 2, ... to a sub n, we can abbreviate that sum as the summation k equals 1 to n of a sub k. Please make sure you take the time to review all of the notes provided for you on the sigma notation.